Welcome everybody to the ASQ Phoenix monthly program. We like to start out every meeting once the networking done is see if there's anybody here for the first time joining us and introduce yourself. Do we have anybody new that hasn't already mentioned? We also have an active program to engage more students. We are working with Arizona State University, connecting with their incoming freshmen as well as their grad students. ASU has a program that they call Capstone Ambassadorship, where they connect with local companies who are looking for some help on projects. These tend to be Six Sigma and or Lean projects. And the grad students have had some level of coursework. So now that they've got the textbook training, they now can lend their resources to local businesses who might be short-handed, and then they get the experience, which helps the business, it helps the students, and it's a good link and tie-in for this section as well. And we're looking to expand that program beyond ASU to Grand Canyon University and Northern Arizona universities. Always want to take a poll if there are any students joining us tonight. And on the registration form, as you noticed, it's where we ask if there are any students. And as I was mentioning, for those of you who did break away for some of the breakouts, we do have an exciting program coming up in August and in October, where our guest speaker is a professional from LinkedIn. She's also a career coach and an executive consultant, and she will be giving us tips and suggestions on how to build that resume and how to write that cover letter that will get noticed by the search engines and AI and hiring managers. What are they looking for? What are some key words? How can you build a tool set that will get noticed? And then also we'll have tips for interviewing, effective interviewing, to secure that next interview. So those are coming up in August and October, and we have more information coming out here shortly.
Hi, I just have a question. Are we still doing cover letters? Because I thought every time I've applied for a job, nobody's ever asked for that. So just bringing that out there
Nobody has asked for,
for
pardon?
a cover letter. Like nowadays, most companies, because I just switched jobs in February, and all they did was fill out our application on the company site.
No. As far as I know, there are still people conducting interviews and looking for resumes and cover letters. Yeah,
Some do, some don't. It depends.
probably depends on the size of the organization and if
Right.
they have a human resource department, or if they're outsourcing that role. They may be using other services that do some of that screening for them, and then that third party then submits the screened applicants. So this is a way to help you get noticed. We've had quite a few calls for that type of a content, given the local state of the economy. So this is our membership team, and the main reason I post this is we do have an opening. So if you are a member of the Phoenix section and you would like to become more involved, perhaps develop your own personal leadership skills, you don't get that opportunity in your current position, this is a way to get a leg up by participating on a not-for-profit organization such as ASQ. So we do have a couple openings. One is our placement chair, which is all about helping our members find that next job and to have a more effective placement process, and also special projects in our section. We work with the ASQ Lean Six Sigma conference because it's actually held right here in our backyard. And so we participate on the planning committee. And so if there are people out there who would like to participate in planning next year's Lean Six Sigma conference. That team or committee will be starting up here in the next month or so. So we would like to have representation and participation from our section members. So there's an opportunity for you here. And we do listen to your input every month. After the program meeting, we send out a survey asking for your feedback and suggestions for future topics. So we do capture those, we do keep inventory, and this helps our program chair look for speakers and topics and things in areas that you're interested in. As I mentioned here, next month, we have one specifically to address resumes, cover letters, and interviewing. We do have a scorecard that we monitor our progress. These are over and above our operational things. You know, every month we deliver program meetings. Every month we deliver a newsletter. Every month we have a member leader meeting. But those are operational. We're also focused on strategic things that we can deliver that are new, exciting, maybe improving our processes. So we've got a list of those different projects. And this is just a red, yellow, green, and blue would indicate that it's done. A scorecard that we can track our progress. And last year we hit 100% achievement, and I think we're on track this year. A lot of things are already green and or blue, so we're tracking quite well. So a little bit about tonight's presentation. John Lindland joins us. He is our current voice of customer chair in the Phoenix section. He has a wealth of experience in the automotive industry. Comes to us from the Detroit area. And John's topic this evening is on 7 failure modes, and then also discussing a tool called the Matrix FMEA. So a little bit about John. He has 35 years of applied experience in failure mode and effects analysis, quality methods, applied statistics, root cause analysis. He has worked for Ford Motor Company, Key Plastics, and was an international consultant for 21 years. He's also has a master black belt and is a global design FMEA lead. John is also the author of these 7 failure modes, and 7FM with Matrix FMEA became the global approach. So he has worked with Chrysler on their Pacifica program, where they took the concept to validation and accomplished it in just 3 years and launched with 60% fewer quality problems than other vehicles in its class. So about the methodology, as John says here, the 7FM is more than just 7 ways a function could fail. It's about the sequence of functions from inputs to primary function outputs. So it's really an understanding of the functions and how their requirements relate to one another, given that a function's requirements are its conditions for success, and that the outputs from that previous function are the subsequent function's requirements for success. So each function will tell you about what it needs to be successful and what happens if it should fail. And I'm not going to read everything. You can read that for yourself. But continuing on, John says the effects of their primary failure modes will be prioritized for failure-based testing, and the most likely functions to fail create the most likely primary failure modes. And as John says, there really are 3 key matrices. They are relational, criticality, and of course the risk prioritization number, RPN. The most powerful matrix is relational. The most important for design improvements is the criticality, and RPN is used mainly to improve your testing. So he's going to be discussing the 7FM and the Matrix FMEA. So with that, I would like to turn the podium over to John for his presentation this evening. And again, if you have not had an opportunity and you would wish to do so, you can find his presentation on our MyASQ website, and the link is provided here. So just go out to MyASQ, search for the Phoenix section, go to the Files tab, and you will see that presentation there, which you can then view and download. So John, take it away.
Thanks, Bob. I'd like to thank everybody in the Phoenix section for giving me the time to talk to everybody. And I would like to invite anybody who wants a better understanding, a little bit more time, maybe suggestions for your own applications, please contact me. I'm a trainer, I'm a consultant, but primarily right now I'm an author. I'm writing a sequence of books on design for functional safety, the safety of autonomous vehicles. So I'd like to begin with, I'm going to share a few different things. This is the materials that I have here. Bob has a copy of these in a PDF file. You can download them, you can use them. If you're going to take a portion of it and put it into a different document or presentation, I just ask that you reference the source as the 7 failure modes and myself as the author. I normally start off with a question when I'm working with teams. And we have such a large group that in 1 hour, I couldn't even get through this first slide in 1 hour if I let everybody have a chance to talk. And so what I'm going to do is I'm going to, hopefully if I can stop sharing. Okay, I'm going to do new share. And I'm going to go to a page that looks like this. If we start off with an air filter, what are the failure modes for a home furnace air filter? And having used in my earlier years in the 1980s, I go back a long way, we would say, what are the failure modes? And people would quickly say blown filter, burned up blower motor, deformed filter, damaged filter. We would end up with a whole bunch of failure-based failure modes. And I found that to be very, very inefficient in many ways. Now, if we would say that the function itself was different, what if it's removed particulates? Well, that's the time where the filter starts working to the time that it ends working. You're never going to start off with a blown filter, so the filter is going to occur afterwards. You're never going to start off with a burned up blower motor, so that's going to occur after this function. Damaged filter, it's going to occur afterwards. You can damage it installed, but the filter never had a chance to perform. A deformed filter happens afterwards. Do not change the filter in time. That's going to be the problem of the owner. Dust built up in the system. That's after the filter is blown. Excessive dust in the house, that's after the filter has failed to do its job. Excessively load filter is after. Filter does not fit the frame, that's before. Filter's not in place. That could occur before or after. So let's say that it's not a bad design to begin with, so it's going to happen afterwards. So all of these can, it's pulled out of the filter, warps under pressure, that's an effect. High humidity is a cause. Installed backwards, well, that's not the filter's fault. Lack of airtight filter around the filter, that can occur in use or after use. So I'm going to say it was good to begin with. I'm just begging the argument, a large particulate built up on the filter. Tear in the filter medium, that's going to occur towards the absolute end of failure. And too low of an airflow through the filter, that's going to occur after it's completely loaded up. Wrong filter, wrong size filter. So let's take a look at a different set of things and say that the filter itself could be fail. Failure modes are functions that enter the fault state. Remove particulates is the function. So let's say that we have these as potential fault states, which are the 7 failure modes. So I'm going to bring these over here just for conversation. And we're going to go through each one of these ones in a little bit more detail later. So I'm just saying hello and starting the conversations. If we play with just one of these 7 and we try to relate some of the causes and some of the effects to just some of these 7s, let's say, excessively remove particulates. We're going to have a blown filter. We're going to have a blown motor. We're going to have a damaged filter. We're going to have a deformed filter. If we're excessively removing particulates, we're not going to have dust built up in the system yet. We're not going to have excessive dust in the house. We will have an excessively loaded filter. Lack of airtight around the filter, yeah. Lack of an airtight filter, that's going to happen. Large particulate buildup on the filter, yeah. And we're probably going to end up with eventually a torn filter. It's going to get so whacked out of shape. But too low of an air volume, yeah, all of these are going to occur. So all of these will relate to just that one little happy note called excessively removed filter. So if we take a look at the filter if we don't change the filter in time, of course, but that's not the filter's fault, but we'll blame it on the filter anyway. Filter does not fit the frame. Yeah, if we're excessively removing particulates, we're not going to hit it. If we have too high of humidity. So basically, what this allows us to do is say if we're excessively removing particulates, we can look at the design parameters that create does not remove particulates. We can take a look at the effects, and we could very, very quickly end up with relating things. So 7FM design FMEA. What is knowable and definable when we start studying a design? 100% of the design functions can be identified every single time. 100% of the function sequences and their interrelations can be identified. 100% of all failure modes are foreseeable and avoidable. 100% of requirements for the parameters for each functions that produce a function, they're all knowable. It's almost impossible to go through 7FM without identifying all of the functions that you need to optimize. We don't look at tests in 7FM to begin with. That's the last thing you do. We look at design parameters. What is the function? What are the failure modes? What parameters will minimize the chance of a failure mode? What are the requirements that the function must satisfy? What are the degradation factors that can cause changes over time? There are 5 categories, and they are in order of importance: temperature, vibration, chemicals, debris of different types, and radiation of different types. And we have dimensions make the function work. We have materials make the function last. These are 2 axioms of 7FM. Dimensions make a function work. Materials make the function last. Energy density. If it's too high, the dimension is going to change, and whatever function it's supporting is going to change and eventually fail. Almost 100% of all potential causes and how they can create a failure mode. Not all causes are knowable and definable to begin with. Some of the causes are beyond anybody's body of knowledge or anybody's experience. But since you can identify the failure modes, you can always identify what's most important for monitoring. And effects that each failure mode can cause are knowable. Conversation begins and ends with a function. The function is a verb and a noun. A function has a clear description. A function has requirements it must satisfy. The first level of effects are each of the requirements not being satisfied. The function has requirements for success. The immediate reason a function degrades and becomes into a false state is one of its very specific requirements is not met. So they are always easy to tag the requirements not satisfied and the requirements for the function not satisfied. The linkages are almost always it's like a laser, it's very definable. Functions have a hierarchy. I'll give you an example. Materials are support dimensions. Dimensions support the component. The component produces how components work together, which are assembly level functions. Assemblies working together to give you systems level functions. systems working together give you a super system level functions, and they're all studied at their own level. And you can't study them all together because of the geometric growth rates. Functions work together in a time sequence. When all functions are good quality, all functions are satisfied. A design is reliable when all of its functions last the required length of time when exposed to all degradation factors. The materials last, the dimensions last, a component then doesn't degrade too much. How a component works with other components in the assembly functions. They don't bother each other that any of them quit at any time. Systems work, super systems work. So functions have a time sequence, and function 1 is good, function 2 degrades, function 3 is bad because of function 2, function 4 is bad because of function 3. And so you end up with a function sequence that turns into a fault sequence. Now, if we identify that function 2 is the bad one, this is a second DFMEA, which is the culprit that most likely fails. But we need to take a look at these things in a time sequence, and the conversation begins with and ends with a function always. Functions and its requirements. Remove particulates. If we excessively remove particulates, this is going to get violated. Reliability is going to fail. Performance rating for airflow will fail, but these two probably aren't going to fail as far as excessive removing particulates. But 1 inch of water gain, pressure drop across the filter at its rated flow rate will fail. Minimum efficiency is not going to fail. So some of these will fail if you excessively remove particulates. If you incompletely remove particulates, others will fail. And the reasons for failing are going to be for removing particulates, whether it's omission, excessive, incomplete, erratic, uneven, too slowly, too quickly. The reasons that the failure mode is going to occur will first come from these. Some of these were not met. So which ones were not met well enough, and what can we do to make them last longer before they fail? All functions fail at a moment in time if you ask it to work for a long period of time. So these are all conversations that are all knowable. So we have four different types of capture mechanisms. We have how they all work together. Those will relate to these requirements, and the depth of penetration is going to be defined by the early fibers are all loaded up, so the later fibers are starting to load up, and we're going to get a deeper particulate penetration. This structure works for every single function of design. This structure works for every single function of process, for process FMEA. So the potential effects are, first levels are here at the conditions, the requirements. The first level causes are all here, and that gives us our conversation. For system engineering V diagram, verification, if we do all of these, satisfy all of these requirements, we will satisfy the system level. If we satisfy the assembly level requirements, we'll satisfy the system level. If we satisfy all of the component levels, we're going to satisfy the filter assembly level. Components are tested before assembly. Assemblies are tested before the systems. Systems are tested across before, and we have to satisfy all of the systems before we have a home system integration. So when we do the test of theory, we have all of the requirements for the system that we need, and then we have all of the requirements of the air filter assembly. If we do all of these, we're going to satisfy all of these. That's a conversation, but how we're going to test is going to get in with quality, what equipment, how are we going to trick it to make sure that we've tested it all. This is a very long conversation. I could spend an hour to 2 hours just talking about this. And I'd love to get a hold of me. I would love to talk with any of you and share ideas. I like people, I like sharing the ideas, and I'd like to help everybody improve. We begin the conversation of sequence with the functional block diagram. So this is an HVA system, and it sits within in this example, a home, could be an office. And we have vents, we have air returns, we have the filter, but the blower is the start of energy. Without the blower, there is nothing that can work. Then if we're going to heat, the second type of energy is add heat. If we're going to reject heat, the second form of energy is to reject heat. So these are the three energy sources for this system. The blower creates airflow, the back pressure creates air pressure, the furnace adds heat, the AC evaporator rejects heat, the air duct transfers the heat, it's a transfer function. The vents provide air conditioned air to the different spaces inside of a home structure or office building structure. And it collects it in its natural way, and then it returns the air and it supplies air. And that's when you get a chance to remove particulates. So the conversation we've had so far is only this component, remove particulates. Now, I can work with any team, and any team can learn to do this very, very quickly and elegantly. It's a very powerful technique. You can assign the 7 failure modes directly to the functional block diagram, and that turns this into a fault state diagram. The fault state diagram can then be used to identify all rational potential effects and all rational potential causes, with the exception of temperature, vibration, chemicals, debris, and radiated energy. The 7 failure modes: omission, no change or response, too much of a response, too little of a response, unstable or erratic response, uneven or biased response, too slow or too fast response. Too slow or too fast only are only a factor if your function is active, if it's challenged to perform and it has to perform within a certain time period. There's a special category of structure related too slow and too fast. That takes too long to fill the structure. It fills the structure too quickly. And for example, shock absorbers on a car, if it responds too quickly, they're too stiff. If it responds too slowly, it's too soft. So each one of these has a different conversation and a way of understanding. And these are the pictures that they look at. You really have to think about your own functions, and you have to take a look at these 7 categories before you can begin to understand function-based failure modes. These are the 7 categories that I developed in the 1990s. It became an error-proof and mistake-proofing article that won the Cecil C. Craig National Quality Award. I can't remember when I won that, but it was very nice. It was a nice compliment. Then these became the 7 failure modes. So let's take a look. If for remove particulates, it's a reactive failure mode. It's not active. You're not challenging it to do it within a certain time period. So it's never going to have too slowly or too quickly. Does not remove particulates, successfully remove particulates, and completely remove particulates erratically and unevenly. If we take a look at these in order, uneven will happen first. Excessively is going to happen second. Incompletely is going to happen third. Then you're going to end up with a loaded system, and it's going to become erratic. It's going to start popping off of its seat. It's going to pull itself off of its seat. Then it's going to let a burst of air pass through it, and it's going to snap back in position, create on the dirty side, a really big, noisy, dirty mess. And then it's going to, again, go into excessively remove particulates, and it's going to do that a certain number of times. Then it's going to break, or it's going to come off the seat permanently, and omission is going to be the last one. What I just said was, you can always predict the order of the failure modes migrating. Some of these are mutually exclusive. You can't excessively and does not at the same time. You cannot incompletely and does not at the same time. You cannot, so there's an ordered structure that takes a while to learn. Select the failure modes in a simple example. So right in here, if we would go over every function on the functional block diagram, we would end up with a pattern that would look something like this. For the sake of argument, let's assume that these are reasonably good starting points for conversations. Now, once we have all of these, we can assign them to a functional block diagram. And so these are the shorthand for the fault states. I developed these in about the mid-1990s, working with the U.S. Army on tank munition design. And they said, well, what are failure modes? And I said, well, it's an omission of a function or the function is done poorly. And that worked for a couple of sessions. And they started getting smarter and say, what do you mean by done poorly? And then I kept describing, we kept having conversations. And I eventually remembered I wrote something that was written in the late 1940s, and it became failure mode effects and criticality analysis. And it had failure-based, it had some function-based, but they weren't separated very nicely. And so I ended up, by the end of the conversations, with some failure modes. What I'm going to do is I'm going to stop sharing here, and I'm going to share a different screen for a second. Let me find this one. Here we go. No, not this one. Do I have a Visio? Hang on a second. Yeah, I do. Let me see if I can't find this. Show all windows. Okay, there we go. This is the one I want. So if we start out here at the end, it's often nice to work on the primary failure modes. So provide conditioned error as primary. If we're incompletely providing conditioned error, that can be caused because the air duct is constrained and we're incompletely giving the error. Otherwise the air duct is just a pass through. Whatever happens here is going to pass through the air duct. So they're not always linked. Sometimes we have pass through. If we incompletely reject heat, it's going to be an incomplete conditioned error. If we excessively reject heat, it's going to be seen as also as incomplete conditioned error. And if we return gas, send refrigerant, incompletely send refrigerant, excessively send refrigerant. You see, we can go backwards through this structure, and in a matter of minutes, we can identify everything out here that's going to reach here. Now, that's a huge amount of detail, and this is for an example only where matrix FMEA comes into play. Matrix FMEA allows you to very quickly, in a matter of 4 hours or 8 hours, go through an extremely complex system design and really nail it all down. So this is just the conversation, multiple causes, multiple effects. And I'm going to go back to the presentation. So that's basically, this is a fault state diagram. It's incredibly useful. You can say, well, if I incompletely create air pressure, I'm going to incompletely add heat. I'm going to excessively add heat. The heat's going to get much hotter. Oh, geez, that's going to degrade material. And it's moving too slowly across the evaporator coil. That's going to give it too much time. If there's any humidity, it's going to build up on the ice coil. It's going to load up with ice. My goodness. You see, we can go through these conversations, and the fault state map, this is the 7FM technique, is the only one that has such a fault state map. And you can dance with this and learn so much about what you're designing. It's just a thing of beauty. But we'll get to that with the matrix FMEA, because to do it all at once is too complex. Causes, failure mode effects. Causes occur before or during the function cycle of the mission. Causes are conditions for success have not been satisfied. The function degrades, it does not meet the requirements. So it starts off with incomplete, becomes even, becomes erratic. So what are the migrating failure modes? Which are mutually exclusive, which migrate and become worse and worse. And by the way, when you understand migrating failure modes, you focus on delaying the design changes that delay the first one. If you can delay the first one, you're going to delay all others. So it's a very big topic. But if we have the failure mode, we have the function effect. The first function effect, first level effect, is always failed to meet the requirements. And then following effects that we saw on the fault tree diagram, or on the fault state map, all the way down to effects on the customer, dust in the house, no heat, no cooling, failure to meet requirements. The air pressure is erratic, it's noisy. If the airflow is too high, you're going to have noise, and so on. Then you also have noise, odor, thermal events, and the risk of injury or death for effects. So we have effects. If we do not remove debris, we have debris erosion. It's making it all the way through, so it's obviously bouncing off of things. It's no longer working as well as it should. And the medium is going to degrade. It's going to degrade. It's going to load up. It's going to become weaker. So you end up with a blower debris buildup. You end up with heat exchanger buildup. You end up with the AC evaporator buildup. You have allergens in the house. You have buildup, and so these are all things which are directly assignable to each one of these. Now, if you know that it starts off with uneven, then it becomes excessive, then it becomes erratic, or if you know the order, it's just a fascinating conversation to have. The causes. These are the requirements for the function success. The first level causes are always one of these begins to fail. One of these begins to fail because of degradation factors: temperature, vibration, chemicals, debris, radiation, waves. Now, what I'm not covering tonight are the three factors that control all functions, and those are energy. Without energy, you cannot have a function. The structure that guides energy to the point of use. Without that structure, you're never going to focus and have a good function. And then you have resistance to energy transfer or movement. These are the three things that control the quality of all functions, even at the micron semiconductor wafer fab level. All functions are controlled by these things. And I can cover all of these. So if you end up with does not remove particulates, you have no energy, you have no structure. You have excessive resistance. If you're excessively removing particulates, so on, you can keep on going back into those same categories. That will dance you, that will lead your conversation immediately into your design parameters. Risk tables. These are risk tables. I'm not going to spend much time in these. I'm going to mention a couple of points only for conversations. If a function is eliminated, all effects are eliminated. If you improve your design, the functions will fault at a later time period, but they're still going to fault. If you can make them fault well after the warranty period, the customer is always going to be happy and say you're very good, and all of my friends are going to buy your product too. So you can delay it, but what you can't do is eliminate the severity. As long as the failure mode exists, the severity is linked to the failure mode. Occurrence is a function of the design parameters. Good parameters change very, very slowly. Detection does not improve the design ever. The RPN, when it comes to design, is the biggest thief you'll ever see in your company, because the only way you're going to improve that is by getting a better test. And I'll show you in a short conversation why that never will work. You cannot test your way to become best in class. You can only design your way to become best in class. See, if your design becomes pretty good, detection does not improve the design. It might find a failure, and it can be improved by working on occurrence. A good design requires a larger sample size. Your company will never afford it. You don't have the time, you don't have the money, and you don't want to become the best testers in the world. You want to become the best function design parameter designer in the world. The Chrysler Pacifica had the smallest fleet size for testing ever. It launched 60% better than any other minivan in the world. We didn't do that because of testing. We just said, here's the failure mode. What are the design parameters that will delay the start of this failure mode? What are the parameters that create the function? And we spent all of our time talking about that. We didn't even really spend a lot of time talking about occurrence numbers or detections or severities. It was always what caused the failure mode. We have a function, we're designing a function. You can design a perfect function always. And you can make that delay as long as absolutely possible based upon technology that you have today. These are always true statements. That's where the conversation becomes powerful. Severity of a 9 or 10 are safety and regulation concerns. Severity of 7 is a poor quality function. The 6 failure modes of excessive, incomplete, erratic, uneven, too slowly, too fast are 7s. An omission is an 8. And when you have them, if they lead to safety and regulations, if this was a medical air filter and it stopped performing well enough and it started letting viruses through or bacteria through or allergens through the system, it's safety critical. Now, if you have a pressure regulator across the air filter, and you can notice a change or fluctuation in air pressure across the air filter, and you have warning limits, it says that we've learned that this means it's a bad filter. If you're in an operating room, I hope you have a secondary filter system. As soon as you notice that the first one fails, then you have a second primary path for good, trustworthy filters. So you can design it to fail safely always. Autonomy. If one camera is failing, you automatically can detect it and you go to the backup camera. Autonomy, autonomous vehicle driving. If you have one primary big computer that's doing all of the graphics processing, and you detected that the functions are degrading there because you're testing it on that one system, you automatically switch to the backup system, and you do it so fast that nobody on the road will ever be threatened. Now, if you no longer have the same critical characteristics for like ASQ, which is the highest safety critical factor, well, then you safely park off the driving surface while you still have full control. So all of these are all driven by knowing how to deal with the function. One thing I mentioned, if your severity occurrence number used in the number strategy I use is 35 or greater, if you ever go to the marketplace with that, you're going to lose a lot of customers or you're going to end up in court. Always for sure and for certain. If your criticality number, severity times occurrence, is 20 or less, everybody that uses your product is going to convince their friends they've got to use your product. This area right in here is what you work on. Now, occurrence numbers must be objective. You cannot sit down and say, well, I haven't seen it recently, so it's a 1. Occurrence is 1. That doesn't work. You need a mathematical model and you need objective data. If you don't have it, well, then focus on your causes, get your best design parameters, and start counting real numbers after you launch. But don't play games and think that you have a criticality number or an RPN, because you don't. That's a for sure and for certain. You need a model. So documenting risk numbers, you have severity, which is always the number 1. And then severity criticality is you can't change the severity by design. You can get rid of the function, get rid of severity. But if you have the function, you're going to have the failure mode, you're going to have the severity. You can make a wing on a jet fall off less often, but if a wing falls off on a jet, it's still the same severity. So with this, with the highest severity for a given failure mode, you pick out the biggest criticality, the biggest occurrence number, and that becomes your criticality. So here you have a criticality of 40. If you have function fault detections, if you've got a system and you've got sensors, and you can measure the function directly or indirectly almost all of the time, that's where you can say, if these things happen, we're going to do these. So in autonomous vehicles, it's always going to be, let me go to a backup resource as soon as I have the identify the function is faulty. And then if you go to a backup source and you only have one, you better be getting off the road, because if that second one fails, you're driving blind and stupid, and somebody's going to die, and you're going to end up in court, you're going to lose. So these are things that allow us to play what if and design all of the bad things that can happen to begin with. So fault detection, safe state. Fault detection, fault mitigation. Okay, so then we end up with preventions. This is where you spend your time. The occurrence numbers, the severity numbers, those are not the conversations you want. You want to describe very clearly, does not remove particulates. Why? Because the filter is not sealed. Well, the filter to frame seal guidelines. If you don't have enough surface area for contact, it's not going to seal. Now, whenever you seal, there are two criteria for a seal. One is the seal and the other one is a sealable surface, and both must be designed. And you can design it where this thing will always seal. There should never be a time where it doesn't seal. The cardboard is softer than the base. The cardboard deforms to the base. The cardboard is a seal. When you have a seal and a sealable surface, you always have a harder material and a softer material. So if we're creating fuel cells, I've done this on fuel cells. If we're working on ocean-going vessels and reliability, you can do it there. It doesn't matter what the design is. As soon as you know what the failure mode is, and you know the design parameters, you can always pick out the causes. So now we're having these conversations. Should we work on it? It's only a 3. Yeah, because it's a 3. Blown out medium. Should we work on it? Yeah. How can we delay on it? Well, we can't let it fill up as fast, so we need more surface area. So we need more folds in the filter, and you know, we have a 2-inch filter. It's a 30-inch, 30 by 20 inch. I'm going to turn it into a 4-inch filter. It's going to take twice as long to fill up. I'm going to double the number of folds in it in the same filter size, and I'm going to have twice. So you can always follow these things. I can make it where the blown out media doesn't occur until twice its current level. You can too. All of you can. So those are the conversations that you want to have. Those are the important conversations. Detection of the failure modes, not the effects. These out in here, the first thing you want to have is function tests, particulate capture simulation, back pressure versus loading. So you're putting all kinds of debris in it, and you've got a sensor across it, and you're asking yourself, with this known amount of contaminated air, how long does it take to fill up? Function degradation tests, fault injection reliability tests. All of these have to go back to the filter. These effects, they do not mean this failure mode occurs. These tests say that the failure mode occurs. When the failure mode occurs, you end up with these effects. If the failure mode occurs and you see these effects, they are related. Until you have the failure mode, you do not know if the effects, in fact, relate to the failure mode. So you don't do effect-based testing and infer back to the function. You have to know that the function itself has failed. Go into the matrix FMEA scratch pad. Chrysler Pacifica. has a power converter module. And it was designed in Italy by a very good company, and it was put onto the transmission of the Chrysler Pacifica plug-in hybrid electrical vehicle. And it wouldn't make its way around the test track more than once or twice without failing. And so I got assigned by a few directors in Fiat Chrysler to lead the team through. This right here is the approach we took. We didn't do the full 7FM. We identified the design of the power inverter module, every single function on the board. We identified which of these might fail. And the largest degradation factor was vibration. So that led into, we can isolate any two axes, and we can dampen the third. You can never get rid of all three axes, but you can get rid of two, and you can always dampen the last one. And we found all kinds of very important things, 6 days, 10 hours a day, and there were about 140 critical failure points. They changed the design. It doesn't fail anymore. As soon as the designer went back and they changed the design and they changed how everything is put together. The plug-in hybrid electrical vehicle is, after 4 years on the road, is still in the top 3 in the world. The Chrysler Pacifica that went through the whole entire vehicle went through this. It has just finished its 4th year as the most award-winning minivan in its class in the world. That includes Honda. So right in here, this is the fault state map that we had. Gray is gray. These are causes. Notice where it's gray, there are no causes. Notice where it's white that there are causes. Where it's gray, there are no causes. Now, over here, where it's white, we have effects. So what will cause these failure modes? Omission, incomplete, omission, and erratic. And same thing here, what are the effects that they occur? So you can very quickly create this map, ignore the FMEA form, go right into this matrix. If you contact me and let me walk you through this, I'll give you the file I use and I'll walk you through it. I want to meet everybody. I want to get to know you. I want to know what you go through on a daily basis. I want to share the techniques. I'm 64. I'm going to quit working when I'm 70. I've got 6 years to share as much as I can with people. So it's a conversation of sharing. This right in here is the matrix FMEA. And on the matrix FMEA, this first one is relational, the relational matrix FMEA. What I'm going to do is I'm going to stop sharing this, and I'm going to go into the this document, a different document. I'm going to come back in here and find the same pages. That's just so I can zoom in and it won't get all messy on me. Okay. Okay. This first one is the relational matrix. Now, the important thing on the relational matrix is we're designing a function. And these are the functions that we're designing. This is our primary function, and everything that's green here is going to be known. Now, so when we go over here a little bit further to the right, and we're going to have total numbers here, 162, 36, 36, 18, and so on. If I can remember where it was, I'd just show you the Excel spreadsheet. But the crucial thing in here is that come on. Okay. The crucial thing is that by the time we're done doing all of this, we can identify which function here. These are the inputs. These are the design parameters we're designing, the furnace, the filter, the thermostat, and everything else. And these are all of the degradation factors, the specific causes. Down here at the bottom, these are sorted left to right, biggest to smallest. this is the function that has the most chance to fail because too many things to affect it. So that's the first thing that's going to fail. This is the second thing that's going to change and fail. And this is the third thing that's going to change and fail, and so on. These are going to be the orders of failures. And almost every single time, they will track up, these are the primary function failure modes. And these are the ones that occur in order. These almost always track the left-hand side. So this here is how we create the functions and the strength of creating the functions. The strength of creating the functions, biggest to smallest, is here. Which one is across all of the functions? Which function has the biggest impact on the design are the rows. Which function has the most things that can make it required to make it good are here. These are all of the degradation factors down here on the bottom. I've lost my mouse. There we go. Now the next one is the criticality matrix. In the criticality matrix, you can zoom in and see it a little bit better. The relational matrix is the most powerful one. Now notice that this only has primary function and primary failure modes here. Let's see. Oh no, this is it. Oh, there we go. Yes, so these are the functions that are biggest and most important, things like that. And so these are the furnace and the blowers and everything else. The furnace add heat. That those things that can that are required to make it work, and it has the most relationships to all of the functions. And the provide conditioned air is the one that's going to change first. Down here, erratic power, no power, damaged duct, partially particulate, packed evaporator coil, all of these things. These are all of the things that are going to happen, are going to be causes. And so you end up with a degradation factor contribution, total contribution. This is the biggest contribution. It's the one that's going to fail. And this right in here, 205, your primary function is going to fail first is incompletely provide conditioned hot air. Incompletely provide conditioned cold air is second. So it's going to predict which of these fail in order, first, second, third, fourth, fifth. The effects that affect the customer out here on the outside cannot reach set temperature, long cycle times, increased energy costs, low airflow, particulate buildup. That's what we were talking about with the filter. It's red only because we were talking about the filter. And so right in here now, the impact out in here, these are the input impact across the whole design. These are the in-scope impact across the whole design. And down in here, these are the degradation impact across the whole design. So you end up knowing 100% pretty much of everything that's going to be going on with the design here on this document. This is the criticality matrix. The criticality matrix, notice how there are severities up here. Severities for the primary failure modes. Notice how these are only 7s and 8s. Okay, when these occur, the bad things out here occur. And out here we have occurrence ratings, occurrence numbers. These are all based upon research. They weren't grabbed, none of these were grabbed out of the air. They're only as good as the research. So I'm just going to say, for right now, this is for conversation's sake. It's not a perfect analysis. Now, for criticality, if all we did was look at the yellow, if all we did was looked across the yellow, over here on the left-hand side, none of these are red. So these are all marginal designs. If you're close to 35, you don't want to go to market. Well, we got 28s, we got 24s, we got 32 outside air temperature, but you can't control that. That's a design parameter you can't defeat. You can only circulate air and cool it down over time to beat that one. And if you lose heat too fast, you'll never catch up. So let's see a little bit further. If we go over here to the right a little bit, what I'd like to note, I'd like you to notice, see these criticality totals here? The highest criticality totals are bad. Even though you don't have 35, you have 320. Which one does that deal with? Filter, remove particulates. If you can double the life of the air filter, you're going to get rid of a big headache. Internal door opening, closing. But that's the house or that's the building design. I mean, what's it like when you have a 4-inch by 12-inch vent going into your room and you close your door, it's 32 inches and you only have an inch of an air gap? Well, 4 times 12 is 480. 1 times 32 is 32. So you have 480 square inches of air coming in at whatever its rate is, and it's only going to go out at a rate allowed by 32 square inches. It's imbalanced. So how you design the airflow, that's a superstructure. You can't, the HVAC can't defeat that. If the air supply and air return is poorly designed, the HVAC will fail. So, but that allows you to have the conversation, which is the important thing. So right in here, you end up with a 36 and a 36. These are specific horrible design points. AC evaporator reject heat, particulate buildup. If the air filter works, it's not going to happen. Filter, remove particulates. These are both the same thing. They're not scored the same way all the way across, but they're both 36s. And when it comes to this one, you know, you're going to get ice buildup, but particulate buildup is going to become the problem before ice builds up. So yeah, that again lets you know that in this whole system, our starting talking point, for some reason, ended up being the most important thing to talk about when it comes to this. And let's see, I think if I go back to the new share, and I go back to this thing right in here, we've gone through this, we've gone through that, gone through the criticality matrix. The criticality matrix over here on the right-hand side, these are all of the preventions. So now if we go to the left-hand side and we're taking a look here, what are the preventions for 120 volt AC provide power? That's not the HVAC, but there are things you can do. Atmosphere replenished air, that's a house design, but there are things you can do. So if you're designing this system and you're installing it, now you know you need to have conversations with a couple of other people to make sure that you're not frustrating each other. Natural gas, furnace add heat. You have to size the furnace to the house. So what are you going to do here to size the furnace to the house? Blow or create air pressure. Are you going to have a 1-speed blower? You're going to have a 2-speed blower, 3, 4-speed blower. And so these are all things you're going to do to elongate it. If we get down here to filter, remove particulates, that's where you're going to size your filter. And that's where you're going to get your HEPA filter air rate, or one of the other specifications you're going to meet. And that's where you're going to say, this is pretty bad, 36. The filter we were planning on specifying was this. We need to double the surface contact area and put it in the same size of a box for the air filter, or we need to design this for a bigger box. So if you design a 1-inch air filter, you would say, let's go do 2-inch air filter, same cross-sectional area, twice the thickness. You have twice the for the same fold pattern. You have twice the air. Twice the space, the cross-sectional area for the air to flow through. So you're going to drop the air pressure through the filter by 50%. If you go by 4, you're going to cut the air resistance down to a quarter of what it was to begin with. So that's where you have these conversations. You know, is it real? Well, yeah. I mean, it leads you through the conversations. And so then the requirements assigned to, the actions taken, the date, then you put it out in the field and you get new occurrence numbers. You do not assign occurrence numbers after you make your decisions. You must wait until your design's in the field and you start capturing real field data. DVPNR is Design Verification Planning Report. How are you going to be testing for these failure modes? How are you going to be testing for these effects? If any of these effects occur at the customer, you can't test for them unless you simulate the customer in your test, which of course is what you want to do. So in the end of it, this one document, this one page right in here, you remember when we were back up here and we had all of these relationships? We had 3 inputs, 8 elements, 19 functions, 68 internal failure modes, 7 primary failure modes. We have 104 unique causes. We have 196 unique effects. That's all on this one page. So the biggest column, whatever you're doing on testing, you're not doing enough. You want to double or quadruple it. Whatever is the smallest column, if you're spending too much money testing that, you might want to back off a little bit because you might be misappropriating money that should be spent on the more important tests. When you come out and here on the highest column row totals, whatever's the highest row total, you need to dig into the design parameters. The smaller row totals, we're not going to dig into those too much. In the Chrysler Pacifica, we worked on the top few. We did not work on the trivial many. And the top few is allowed the design team to fix the most important things rather than fix everything and hope for the best. It was a very, very fun thing to do. So that's the end of my presentation. I think I was scheduled to end at about 7:42, so I finished a little bit early, and I'm going to stop sharing, and we can go back in. Bob, I'll let you take over.
Great. Well, thank you very much, John. That was a very detailed. I can see where you said usually you're presenting at least 2-3 hours on this topic and more. That's why you invite conversations with people who are interested in learning more how to use this tool.
2 to 4 hours on this would be a really nice hello, how are you? And now I know you and we're friends.
Right. Yeah. But a great overview, because I know a lot of us, when we first learn about FMEA, it's one table, and then scoring risk and or severity and occurrence and detection to come up with an RPN number. In fact, there was a discussion just recently, I'd say within the last week or two at the most, posed by our speaker from last month, Mr. Amitabh Saxena, where he was quizzing people who follow him on LinkedIn about the use of 1 through 5 scale instead of a 1 through 10 to calculate your RPN numbers. He was saying most organizations use a 1 through 5, and I joined in. I said, boy, my experience is 1 through 5 is just compresses everything too much. You really need a broader scale so you have a greater range of scores to really hone in on what's critical. And I see you also use 1 through 10 for each of those categories.
1 through 10 works, but for me, the risk numbers are secondary. They're far less important than understanding the function and talking to the function and say, what are the best design parameters to make you good and last for a long time function? See, when you dance on that, then the risk numbers are absolutely meaningless. Yeah. But they do help you identify on the matrix FMEA where to spend your time on testing and where to do it on for detection and where to spend your time and money on prevention. You don't fix everything. Right. You fix the most important things.
Well, we do have a attendee, Savitri, who raised her hand. Savitri, if you're still with us, would you like to pose your question? Maybe she's not able to mute. Maybe she's no longer with us. I'm trying to get down through the list here.
Okay.
Are you still here, Savitri? See her on the list. She may have had to sign off. Well, hopefully she'll be in touch with you. Are there any other questions from the attendees?
Oh, very well done. Thank you.
You're very kind. Thank you very much.
Thank you.
Anybody wants to get a hold of me and talk a little bit more deeply, please get a hold of me. It's
Okay.
not like I'm lonely and I'm begging for friends. I just like meeting people. I like talking to get to know people.
All right. Yep.
Thank you.
Okay.
Have a good evening.
You too.
Well,
Thank you.
So just the last few follow-up slides on my part. I think I'm sharing. So next month, again, the second Thursday of the month, August 12th, we have Linda Baugh, who is a Chief Career Officer of ACE Executive Careers. And she's also an expert on LinkedIn. And Linda, in August, will be discussing overall branding and positioning for job search and internal advancement, talking about resumes and cover letters. And then she will also be using part of that time to discuss interviewing and how to get to the next step in the process or to that job offer, and then how to negotiate the offer. So that's coming up in August, and it'll be a more or less a special program because to cover all of that content will probably take close to the 2-hour time frame. So we probably will not have the customary 30-minute networking session. I want to give her the full time allotted for that material. Just a reminder that you will be receiving an evaluation survey from John, again, our Voice of Customer Chair. If you could please complete that survey, let us know how we are doing and any suggestions for future topics. And then along with that link to the survey, you will then receive your recertification unit certificate. I was mentioning to the people who had not broke out or participated in any of the breakout sessions we had before the session started that we do have some allied partners, and one of those is Sway, and they have a free webinar coming up next Thursday morning on how to blend ISO and Baldrige to achieve performance improvement. If you're interested and if you do use Minitab, they are also having a webinar next week, July 14th at 9 a.m. on a new tool they are launching called Graph Builder, where you can build multiple visualizations, and they're seamlessly updated. And so it's a 30-minute presentation on that new tool that they have launching. And then the SCORE is a local organization that works with small businesses. And they have a special session coming up on July 20th to know more about how to use finances or how to understand finances within a business. And it's very important for us as quality professionals to know how to read a P&L statement and a balance sheet so you can calculate the cost of quality. So if you'd like to learn a little bit more or take it as a refresher, we have a free webinar offered by SCORE on July 20th. And again, there are a number of ways that you can connect with us here at ASQ Phoenix. We have a Facebook account, a LinkedIn page, Twitter, Instagram, YouTube. And again, these presentations and recordings are available to you through our My ASQ site. So with that, I would like to thank everybody for your time and attention, and we hope to see you next month.
All right. Good evening.
All right. Thank you very much, everybody.
Yeah, thank you.
Thank you.
Have a good
Great.
evening.
Thank you.
Thank you. Bye-bye.